This is one of those lessons that's very hard to visualize. So I'm going to do my best to kind of make it come alive for you as much as I can. I kind of make it in 3D on two-dimensional paper. So the line y equals 2/5 x is rotated around the x-axis and a cone is created. So this is the line. The dots on your graph aren't very clear, but that's okay. And what we're going to do is take this and rotate it around. I had drawn this earlier, but I'm going to draw it a little clearer now. So if I had that line, first of all, I could find that area. I could find that area pretty easily. And that area is, well, it's a triangle. But if we wanted to go all calculus on it, which we'll have to do on some shapes, if we wanted to get all calculus-y on it, that's not a word, then we would say it's the integral from 0 to 10 on the x-axis of 2/5 x dx. I'm going to put parentheses around that for reasons that'll become clear in a minute. So that's really what it is. We could do that in our head. We're not going to. Or we could just look at the triangle and say, well, you know, we could figure out the area of that triangle. However, here's the deal. We're going to take this and we're going to rotate it around. We're going to basically spin this around and make a little circle out of it. I know that looks more like an oval, but what we're doing is we're taking this shape and we're spinning it around and it makes a cone. If I could draw it right. It makes a cone. And that cone has a volume. Now, I can figure out the volume of a cone. That's easy to do. There's a formula for that. However, when I spun this around in a circular fashion, then I created a solid. So I took this two-dimensional shape and then I rotated it around and I made a solid out of it. And I'm pointing at pi r squared because that basically is the formula for what we're about to do. This is the area right here. But I took that area and rotated it around as a circle. And so I'm just going to multiply this by pi. And this, at any given point, is my radius. Any given point where? Okay, so here's what's going on here. This is a radius for that circle that got rotated. This is a radius for that circle that got rotated. This is a radius for that circle that got rotated. And so we have pi times all those radii squared. And that is going to give me the volume. And we're just going to find it like that. And we could do this without a calculator, but we're not. So I am going to leave the pi off, though. So 9, 0 to 10 of 2/5 x squared. And I'm going to need another set of parentheses around that. 0.4x, there we go, and then dx. There we go, that's it. 53.333333 pi, let's turn that into a fraction. 160 pi over 3, you can turn it into a crazy decimal if you like. I'm not, I'm going to call it 160 pi. And that is the volume. And what are the units on volume? Well, it's cubic units, but we don't know if it's inches or centimeters or whatever, okay? So now we're going to do the same thing, but it's not the same thing. So it's about to get a little bit trickier, but we're still going to use pi r squared. So find the volume of the cone that is created by rotating y equals 2/5 x. Let's just stop and draw it again. Stop, draw it, there it is. All right, but now we're going to rotate. I'm going to erase that little line right there. We're going to rotate it around the y-axis on the interval from 0 to 4 on the y-axis, okay? So now we're going to take this and we're going to swing this around this way and we get this cone instead. So at any given point, this is the radius, or this is the radius, or this is the radius. So no longer do I need to talk about y equals 2/5 x. I don't need that. This is y as a function of x. Now that I'm rotating around the y-axis, I need x as a function of y. This is what I will use. That is my radius, okay? So again, pi r squared, same idea. We're going from 0 to 4. We're just on the y-axis now. And it is 5/2 y, and that is all squared. Integrating with respect to y, don't forget your pi. And again, this is area. Pi times the area squared. And that's the radius squared. And that's the area of a circle. And that's really the best way I know to remember this. And so this right here, of course, is my function in there. And so we'll just integrate it. I'm going to leave the pi out of this. Now, don't think it's the same answer as the other one. Notice the difference in the cones. This one went kind of long ways, and this one's up and a little bit wider. So even though they're the same equation, they're rotated in different directions. So math 9, 0 to 4 of 2.5. Let's put it in parentheses. And you could use x. I'm going to be consistent with the way the problem is, and I'll use L1 apparently. And we'll use y. And we'll use that right there. And it's 133.33333. That is 400 over 3. 400 over 3, and there's a pi involved. And you can turn it into an irrational number if you want to, by multiplying by pi. All right, let's not though. An ellipsoid is a three-dimensional ellipse. It is created by rotating a semi-ellipse, obviously half an ellipse, about an axis. Find the volume of the ellipsoid created by rotating the ellipse below about the x-axis. Okay, let me tell you what they didn't tell you. They didn't give you an equation like they did here. They didn't give you an interval like they did here. But everything is going to be implied. So basically, we're rotating this around the x-axis on an interval. So I'm going to just go ahead and start writing what I know. That's one strategy I like to do. Like if I don't know how to tackle it, I'm just going to go ahead and start writing what I know I need to do. So pi times r squared. And when I say r, I'm really meaning the equation, the distance from the axis of rotation to the function itself. Okay? Well, I also know this. It goes from -4 to 4. They didn't have to tell me that. I can see that on the graph. And the thing I don't know is what goes in here. But we'll figure it out. It's relatively straightforward if we remember a little bit of pre-calculus. So in pre-calculus, there's a formula for an ellipse. And that formula, if it's centered at the origin, is pretty straightforward. It is x squared over a squared plus y squared over b squared equals 1. And there's different forms of that. And of course, this is the one where it's centered at the origin, like this one is. And the horizontal distance is 4 from the center to the edge. I'll loosely call this the long radius. That is not the correct mathematical term, so don't go around saying that. But that would be x squared over 4 squared. And this is the short radius, the length of, well, half the length of the minor axis. So y squared over 2 squared. And there we go. Now, we need to solve this for y. Obviously, I can't plug that in there. So we need to solve this for y. It takes a little bit of work, but that's okay. We'll get it. And that is going to be this. And let me drive this point home one more time. As we look at this in terms of pi r squared, the r is the distance from the axis of rotation to the equation itself. So at any given x value, there's my radius, there's my radius, there's my radius, there's my radius, there's my radius. And I do that for all my radii as I integrate, basically. So let's come over here and solve this, and we'll do a lot of it in our heads. So we'd subtract that term, 1 minus x squared over 16. And then we can multiply that whole thing by 4, and then we would square root it. And there are some little cosmetic things we could do to fix that. We could take that out and make it a 2. We could distribute it in if we wanted to and reduce that. I'm going to leave it exactly the way it is. Messy as it is, let's just leave it. It's fine. It's not going to bother a thing. So 4 square root of 1 minus, whoops. Nope, no whoops. Never mind. No, yeah, whoops. I have messed up. Let me get some white out. I should have put that 4 inside that square root. My fault. My whoops was not in vain. Square root of, and then 4, and then 1 minus x squared over 16. If you're noticing what I'm noticing, you're realizing that the squared and the square root cancel, and you're absolutely right, of course. And so if you didn't want to write them both, that's okay. I did, but I'm not going to type them. So math 9, there we go. Going from -4 to 4. By the way, just going to throw this out here. I'm going to go down here for a second and delete that. I could go from 0 to 4 and then double it. Do you see why? It's because it's symmetric about the y-axis. So whatever I get, if I rotate that one, I get the same thing on this side. However, I think that's just an extra step when I could just type -4. So I'm not going to type the squared, and I'm not going to type the square root because they'd cancel, as you know. 1 minus x squared over 16 dx. And whatever I get, I'm going to put a 4 with it. I'll put a pi with it, not a 4. 64 thirds times pi. That is the volume, and it's in cubic inches, cubic centimeters, cubic meters, cubic units, whatever. Okay, we're going to find the volume of the solid created by rotating the region bound by these equations about the x-axis. Y equals square root of x, y equals 1/10 x, and x equals 4. What? Okay, up until this point, everything we've rotated has been hugging the axis, or just like abutted right up against the axis. So this region right here was like, oh, from the axis up to there, or from the axis over to there, or from the axis up to there. But now it's like, wait a minute, there's this empty space in the middle. So we're going to do this kind of in pieces. So let's just go ahead and start with what we do know. We know that much, right? And let's be real honest, we're rotating, so we know that much as well. So let's figure out some intervals. We'll figure out what goes with the integral, and we'll go from there. So we know it starts at 0, and it ends at x equals 4. So if you wanted to, you could draw that and say, well, you know what, this is where it ends, because they said so. I mean, obviously, these do keep on going, but they said stop at 4. It's bound between this, and 4, so it stops at 4. So from 0 to 4, and we got that much. So what this really is, if you were to visualize this actual shape, if you were to rotate it, then it would look something like this. You would have this almost like a bullet with a little hollow cone in the middle. You would have this part that kind of goes around, and it would be like a dome. And then on the inside, you would have this little hollow cone. So the outer radius is this. Now we have to square it, so obviously these cancel each other out. But if the problem just said, find the volume of the solid created by rotating that around the x-axis up to 4, then this would be our problem. I'm going to put a dx way over here. This would be the problem. Wouldn't have that gap there, but it's not. So that would be the whole volume, but I'm going to subtract away this little volume inside that I'm not using, and that volume inside that I'm not using is 1/10 x. I'll square that as well. And I'll put brackets. You can put big parentheses. You can put whatever you want there. And that is what we're dealing with now. Okay? Math 9. Well, let's be very careful with our parentheses. And I'm just going to call that x minus, let's get crazy with it. 0.1 is a tenth, and we square 0.1, we get 0.01. And then we square x, we get x squared. There we go. That wasn't too crazy, was it? I'm going to turn that into a fraction. You can use a decimal if you want to. 584 divided by 75 pi. That is the volume. Up until this point, we haven't really multiplied anything by pi, but that's what it would be. It would be, let's do that one on this one, equal to or approximately 24.463 cubic units. That would be the volume of this odd little hollow bullet type thing.